Welcome to yet another episode of Kinematics, and yes, I know, Bob is still in uniform motion. What a tragedy. Now, I want to take this opportunity to introduce yet another new concept to you, okay? So, I don't want you to be sad. I want you to turn that frown upside down. Alright, okay. So the new concept that I'm going to introduce to you is what we call as a velocity time graph. That's right, okay? As the name suggests, it's a graph which is along the horizontal I take the time and along the vertical I take the velocity. Just like how we took the position time graph, this time we are going to take a snapshot of velocities, not the positions. I'm not snapshotting Bob anymore. I'm snapshotting his velocity. So I'm taking his velocity at every instant of time and plotting it over here. Okay? Now let's see what we have here. These are the things that you have pretty much seen before. This is the equation of Bob's position at any moment in time. This is the velocity equation. It's just the velocity v equals 2. And this is the definition of velocity. Well, this is average velocity, but I've not put the bar here, but because remember, instantaneous and average, the same thing for uniform motion. All this must be common sense to you by now, okay? Also, you can see the familiar xt graph which I've drawn on more than one occasion so far, but we're going to translate this to the velocity time graph. Okay, are you ready for this? Let's begin. To draw the velocity time graph, we need to ask what is the velocity of Bob at every instant of time. Okay, so let's do that at t equal to 0. Alright, so at time t equal to 0, when I started my clock, what's Bob's velocity? Well, let's ask him, Bob, what's your velocity? Well, we know that. Bob's velocity is 2 meters per second. I'm just gonna write that over here. That's 2 meters per second. That means at t equal to 0, I'm gonna plot it over here. Okay, now remember, careful about what velocity time graph is. This is not the position of Bob. It's not very physical. It's not a physical thing. It's the velocity, okay? Next, I'm gonna plot it at t equal to 1 second. I'm again need to ask Bob, where are you? No, I don't care about where he is. Not the position time graph. I'm going to ask Bob, what is your velocity? Well, Bob says, well, it's just 2. So I'm gonna write that again. It's 2 meters per second. Okay, so make a plot again at t equal to 1 second. Velocity is pretty much the same. It's 2. I think you can understand where we are going with this. What is Bob's velocity at t equal to 2 seconds? Well, it's going to remain 2 meters per second. So we're going to make another point over here. Again, don't think that Bob is moving this way. Don't even think that Bob is moving this way. It's not moving. It's not the one-dimensional world that you see here. It's velocity. It's a little bit hard to conceptualize maybe when you're doing it initially, but you'll get the hang of this, okay? And at time t equal to 3, what's Bob's velocity? Well, Bob is tired of telling us. It's 2 meters per second over and over again. So for one last time, I'm going to plot it over here, and I'm going to ask you, what would the graph look like if I plotted velocity at every moment in time, and you know what it will look like. It's gonna look like a straight line. Ta-da! We have done velocity time graph. Is it time to go home? No, not yet, because I want to tell you something very important about the VT graph. Let's first check what we know, what we have understood. Look, x equal to 1 plus 2t, this is the equation of position for this guy, and we have the equivalent graph. Similarly, so you can actually make sense, right? This is a linear equation of time, and you have a straight line. Very good. Now, we have the velocity time graph, which is actually this equation. This equation and this graph are the same things. Can you see v equal to 2? It's independent of time. That's exactly what we have drawn. The velocity remains exactly, it's supposed to be a straight line, exactly the same. It's independent of time. Regardless of what time moment you choose, you'll always find v to be 2 meters per second. So, time to go home? No. Not yet, because there's a key point involved here. There is something in the xt graph which you don't find in VT graph. Let me be very specific about this. See, both these graphs and these equations tell me one simple thing, that Bob is still in uniform motion. That's sad, but that's what it's telling me. However, XT graph gives me some information that VT graph does not. Can you try and figure out what that is? Pause this for a moment and try to figure out what information XT graph gives, but VT graph does not. Okay? Alright, let me tell you what it is. See, XT graph tells you what the position is, obviously. It also tells you what the velocity is. Just look at this number. However, VT graph does not tell you what the position is. VT graph only gives you the information about velocity. It does not give you any information about position. Think about it. If I asked you, just by looking at the VT graph, what is the position of Bob at x equal to 0, and you say, I don't know. You only know his velocity is 2 meters per second. It's similar to asking, what is the position of Bob at t equal to 0 by looking at this equation. You can't do that. You can only tell the velocity is 2 meters per second, but you cannot tell what the position is. You have lost the information of position when you translate it from position to velocity. However, notice that position equation, position function, has all the information you need. It has every information that you want. It can tell you the position, it can also tell you the velocity. But the velocity equation and the velocity time graph does not give you any information about position. Now you may be wondering what's going on, because velocity depends on position, right? No, it does not. Okay, listen to me very carefully, open your ears, do whatever you want, but concentrate. I want 100% concentration over here, because I'm going to tell you something, a huge misconception that many students have, many students, teachers, people have. Velocity depends on change in position. It does not depend on position. Change in position and position are not the same things. They're two completely different things. So here is something I want you to remember. Velocity does not care anything about position. It only cares about changes. Okay? Position and changing position can have two completely different numbers and can have two completely different signs. Position can be positive, but change could be negative. Position could be negative, but change could be positive. I'm going to talk about this in great detail later on again, but as of now, I want you to put this in your head. So, velocity depends on what? Change in position and not position itself. Okay? That's why you lose the information. You lose the information about position in the VT graph. You don't have that anymore. However, you can get the information about changes in position. Changes in position was called something. Do you guys remember what it was? Oh yeah, it is displacement. That's right. This guy, I forgot to write that down over here. Let me write it down. This guy is displacement, okay? So although velocity can't tell you anything about position, it can definitely tell you something about displacement. Okay, so let's work out a very simple problem to figure this out. Here is a question. Calculate the displacement of Bob from t equal to 0 to t equal to 4 seconds. Maybe I should place that somewhere here, because we don't need the XT graph now. Okay, so we want to calculate what the displacement of Bob is from t equal to 0 to t equal to 4 seconds. Think about this for a while. How do we do this? Well, that's actually easy, and we're going to do this mentally because I really don't have space here to write any of this down. So we have delta t of 4 seconds. That's the time interval. Okay, we want to go from here to somewhere over here, which I have not drawn over here. So we have a delta t of 4 seconds. So this is 4. And v is 2. We already know that. So what is displacement? You can do this in your head. Come on. 2, and there's a 4 here. So 4 goes on this side. You get 4 times 2. That is 8. So displacement is 8 meters. So you see what has happened? This equation can tell you that in 4 seconds of time span, Bob has gotten a displacement of 8 meters. That it can tell, but it cannot tell from where to where. Is it from 0 to 8? Is it from 1 to 9? Is it from -4 to +4? this equation cannot tell. It can only tell you what the displacement is. But now my question is, how do you get displacement from the velocity time graph? Okay, not from the equation, but from the graph. Okay, we should be able to do that, and that's easy. I'll tell you what we'll do. We'll mark these points, t equal to 0, that's over here, and t equal to 4 seconds. Let's see, t equal to 4 seconds. We're going to mark this point over here. Okay, and we need to multiply v with delta t. Here v is this length, 2. That is this length. So that is over here. This is 2. Okay, and we multiply 2 with 4, and 4 is this length. On the graph, it's this length, 4. And if you multiply these two lengths, we ended up with displacement. Okay, now I want you to think of this particular graph and forget about v and t for a while, and just tell me what do you get when you multiply this length with this length. Think about it. Forget this is some VT graph. Just think about this as a normal graph, anything. It could be x, y, or something. But what do you get when you multiply this length by this length? Come on, you can do this. It's simple geometry. It's area. That's right, you get area. Guess what? This area represents the displacement. That is one important thing you should remember. So I'm going to note that down over here. Area of VT graph under VT graph. VT gives displacement. It does not give you position, but it gives you displacement. And that is definitely something worth putting a box and remembering it. Remember last time we saw that xt graph can give you velocity by taking the slope. The slope of xt graph gives you velocity, and the area under VT graph gives us displacement. That is awesome. Okay, so now that we have introduced two different graphs, what we are going to do is we're going to try and translate from xt graph to VT graphs and from VT graphs to xt graph. We're going to do some quantitative analysis and have some fun, and let's see whether we're able to digest what the two graphs are telling us. Okay, so let's do a simple exercise, and that exercise we'll do it, let's get rid of all this, we'll do it over here. I have two graphs with me, xt and vt, as you can see, and we're gonna bring in our two characters, Bob. Well, Bob is the star of the show, but we also have Sheila. I really have no clue who Sheila is, but let's see, we have her over here. And here's the thing, I'm going to plot xt, some xt for Bob and Sheila, and I want you to predict what the vt is going to look like. That's going to be the exercise. Alright, so let's do case 1. In case 1, this is what xt looks like for Bob and Sheila. The first step is to try and understand what this is. If you don't understand what this is, I highly recommend you to pause this video right now, go back to our earlier episodes where I discussed xt graph in great detail, and then come back over here. Please do that, that's important. I'm assuming that you have clear understanding of what this is, what this graph represents. What this graph represents is the following. At t equal to 0, Bob is here and Sheila is over here. Okay? And as time progresses, both are moving along the positive x direction. Well, they're going this way. Okay? And if you want to know what's going on with the velocity, you need to take the slope of this. And the slope, can you see? I've put them parallel to each other. They both have the same slope. That means in this example, Bob and Sheila have the same velocity. So, if I were to plot that, I would get the same answer for Bob. I would get exactly the same graph for Bob and for Sheila. That's case 1 for us. I hope you're cool with this. Okay, I repeat, these guys have the same velocity. You may be wondering, but Bob is positioned here and Sheila is positioned there. How is that they got the same VT graph? Well, hello, remember this? Velocity does not care about position. I don't care about position. Velocity only cares about changes in position. So the changes in position per time turns out to be exactly the same because the slope is the same, and therefore the velocity turns out to be the same. So for example, if this slope was 5, then the velocity is 5 meters per second, and Sheila would also have the same velocity. They would be going together. So you can sort of imagine this like two race where Bob is leading Sheila and both are going with the same velocity, going like this. Okay, that's what this represents. Alright, okay, case 2. I'm going to show Bob this way. I'm going to show Sheila this way. I think we have done such a case before, but now I want you to pause the video first and think about what the VT graph is going to look like. Okay, I hope you did that. Let's try to figure it out. The first step is, let's try to understand what is going on with the xt graph. At t equal to 0, Bob is at origin and Sheila is below origin, somewhere in the negative. But you can see as time progresses, Sheila is going much faster compared to Bob because Sheila has a greater slope. That means Sheila has a greater velocity compared to Bob. That's why if we plot Bob over here somewhere, remember both of them have the uniform, both of them are in uniform motion, so velocity is going to remain the same. So if this is Bob, then Sheila is going to be somewhere over here. Okay, this is qualitative, so I really don't know how much more velocity Sheila has. We have to calculate the slope for that, but this is what the VT graph for this xt graph looks like. Okay, case 3. This is going to be a real test of your understanding, okay? Now case 3 is going to be something like this. I'm going to put Bob this way, and I'm going to put Sheila this way. This is Sheila for you. Can you think about VT graph for this? If you do this, then thumbs up for you guys because you have digested VT graphs perfectly. But if you don't, then it's okay. You can always go back, watch more, watch it again, rewind, watch it again, and I have review problems for you, so don't worry about it, okay? Alright, pause the video, try it now. I hope you did it. What's the difference? Well, as we have seen before, this represents a negative slope. You see, it's a downhill, it's a negative slope. So negative slope basically says that Sheila is moving in the negative x direction. That means Sheila's velocity is negative. It's going to be somewhere here. Okay? Somewhere over here. Alright, what about Bob? Well, Bob is still going along the positive x direction. See, his slope is positive, he's going this way. Okay? So Bob's velocity is positive, it's going to be somewhere here. But guess what? Guess what? We can be a little bit more precise with this. Can you see that Sheila, although her slope is negative, her slope is bigger in magnitude? Imagine a dude is trying to climb up here, it's going to be hard for him, and a dude is about to slide over here, it's going to be fun for him. But can you see that the amount of fun that dude is going to have is more than the amount of hardship this dude is going to have? I have no idea whether that makes sense to you. Okay, I think that's a bad example. Let me tell you in simple words. See, this slope, if you calculate the slope that you get over here, is much bigger in magnitude. Look at the angle, dude. Come on, just think about it. Look at this angle. This angle it makes with the horizontal. Here it is. The angle which Sheila's graph is making with the horizontal is much bigger than the angle which Bob's graph is making with the horizontal. Can you see that? I hope you can see that. Alright, that means although Sheila's velocity is negative, the magnitude is huge. So I should really put Sheila somewhere here, okay? And Bob should be somewhere over here. This would be a little more accurate, even though it's qualitative, a little bit more accurate to represent this particular picture. Okay? Alright, and I'm gonna ask you one last question, and I will not solve this for you. You guys will solve it. You ready for this? Okay, this is the situation for Sheila, and this is the situation for Bob. I want you to think about the VT graph for this and do a lot of review problems. I have a lot of review problems in store for you. So I hope I have taught you what VT graphs are, and I will see you next time, so stay tuned.